to talk to you a little bit about how we collect evidence of global climate change from the Earth's ice cover. And on the first slide, you'll see some images of the different places where Lonnie and I have traveled to collect ice cores.
You can see that we're very fortunate to live on a planet where we have many recorders of our path, the climate. And today we're going to talk about one of these recorders, which is the ice cores. All right, so we're going to be looking at ice core records, and we're very fortunate to have ice core records from around the Earth, from Antarctica and Greenland, but also from the very highest mountains, like in the Andes of South America, and from the Himalayas. And in these are a marvelous history of our past.
All right, so I'm going to tell you a little bit about what's on this slide. So in the upper left is a map of Antarctica, which is the Earth's largest ice sheet. In the middle is a photograph of an ice core, and over on the right is a photograph of a thin section of the ice core. And if you look really carefully, you should be able to see bubbles in the ice. And scientists, using special equipment in their labs, can essentially take the air out of those bubbles and then measure the concentrations of different gases like carbon dioxide and methane, which are two of the major greenhouse gases that are currently warming our planet. If you look at the graph on the bottom, you'll see a red line and a blue line. And on your right is today. The axis on the bottom is time. So if you look at the graph on the right and then look to the left, you'll notice that those curves go up and down about 8 times. And this is an 800,000-year record, meaning it's almost 1 million years long, and it's showing you 8 ice ages, 8 times when the Earth was warm like today, and then when the Earth was cold. And what you'll notice is that the red line, which is methane, and the blue line, which is carbon dioxide, go up and down they go up and down together. So when it's warm, we have more of these greenhouse gases, and when it's cold, we have less. If you see on the right side, you'll see the 2 dots or the stars, the red one and the blue one. That shows you what the concentration of carbon dioxide in blue and methane today, or methane concentrations are today. So what you can see is that those concentrations of those 2 important greenhouse gases are higher than they've been in the last almost 1 million years. And then if you just follow the arrow up, you can see how high those concentrations are predicted to be at the end of the current century. So that's 91 years from now. Now, in this slide, we're going to show you how we reconstruct the Earth's temperature history using using oxygen isotopic ratios that are actually measured from the snow or the ice. So in the upper right, you'll see a graph or a map of the world and the 2 red circles. The red circle to the right is over the Tibetan Plateau, where Lonnie and his team have drilled ice cores for the last 25 years. If we take the average of the oxygen isotopic ratios from those 4 ice cores, and then in the other circle we have 3 ice cores from the Andes of South America, and we put those together, we get this green graph at the bottom. And essentially, again, today is on your right, and this is a 2,000-year history. Now, up above on the blue you see the reconstructed temperature history of the northern hemisphere in the blue, and then in the red are the measurements we have. Those are actually using instruments, so that's the instrumental record. You can see how short it is. But the important thing to notice is how similar the isotopic history from ice cores is compared to the curve in blue, which is reconstructed from tree rings and corals and lake sediments, as well as ice cores.
But if you look at the map, we, over the last 33 years, have conducted over 57 expeditions to 16 different countries around the world to collect these archives. I'm going to take you to Peru now with a video so that you can see how we actually recover and why we recover these histories.
This is a country along the west coast of South America, chock full of wildlife, natural environments, history, and culture. It's thought that humans first migrated to Peru over 10,000 years ago, as our last ice age was coming to an end. Early Peruvian cultures rose and fell following the ebb and flow of drought until the Incas. The Incas, who have their roots in Cuzco, Peru, first came into being around 1100 AD. They conquered much of South America, but were known for their benevolent rule. Between the mid-1300s and 1500s, the Incan culture spread, until the Spanish invaded in 1531. Since then, Peruvian culture has been strongly influenced by Europe and the West, but they hold tightly to some of their native roots. There's a steep gradient between those connected to the world market and those living in smaller communities. To this day, many Peruvians tie themselves to Pachamama, or the Mother Earth, from which they grow their foods and use the water resources. Bound so closely to the environment, they're very susceptible to changes in climate. Like has happened in the past, could a sudden change in climate devastate their culture? Are we in the middle of a climate change? There's a lot of evidence out there suggesting that we are. You can see how far back this glacier in the eastern Peruvian Andes has receded in a little over 20 years. How can we learn more about these issues? How can we stretch our understanding further back into the past? Being a climate scientist and a mountaineer, I had the good fortune of being invited on an expedition with scientists from the Bird Polar Research Center who were trying to get to the bottom of some of these questions. Led by Dr. Lonnie Thompson, our goal was to take ice cores from 2 high-altitude Peruvian ice caps.
We can't tell what
in areas where temperatures rarely even approach the freezing mark, snow accumulates year after year. Hundreds, even thousands of years of snow can then be drilled up. This snow is not just frozen water. It comes with other compounds, like dust and salts. The chemistry of snow records the climate from which it came. With these tools, we can estimate what climates were like long before humans even started to record temperature.
It's actually ice already. I mean, ice from the firm, not the ice.
Well, there are several purposes of current expedition. One approach is to build a record cap on the Quelccaya ice cap, which we have documented over the last 20 years is very rapidly retreating. And it won't be too far in the future where this archive will no longer be available to us. And Quelccaya is in the southwestern part of the Andes, and its precipitation comes mainly out of the Amazon basin, ultimately the tropical Atlantic. Corapuna, the second site we're going to, also receives most of its moisture from the Atlantic, except during La Niñas. During La Niñas, it gets precipitation out of the Pacific. And we're hoping the chemistry and the isotopes in the snow coming from the Pacific will have a signature, so that we can compare the El Nino history from Quelccaya to the La Nina history from Corapuna over the overlap period of these two records. This depth, the layers are getting so thin, it's hard to discern them. They look like they average about 1.2 centimeters per year. They give us about 80 years per meter at this depth. This is exactly what we'd expect. We expect to see diameters being compressed more and more as we approach the bottom of this ice cap.